Hello everyone, welcome to this video. This video will cover the first part of the introduction to fundamental electrochemistry series, solvents and electrolytes. This lecture will focus on the types of solvents, the relationship between solvent properties and the solute behavior, the conditions that should be met by supporting electrolytes, the types and the compositions of some electrolyte cells commonly used in organic solvents, and the potential range for electrochemical measurements. The role of the various effects affecting the positive and negative potential limits, solvent and the supporting electrolyte in influencing the electrode responses will be discussed using mercury and platinum electrodes as examples. Other points that should be considered when choosing a solvent and a supporting electrolyte, in addition to the effect on the electrode response. When we talk about solvents, water is immediately thought, and indeed water is a very good solvent. However, there are many excellent solvents besides water, some of which are widely used in electrode reactions now. These solvents can be broadly classified into molecular solvents, which are mainly composed of molecules, and ionic solvents, which are composed of an anion and a cation. Molecular solvents can be divided into two main categories, aqueous and non-aqueous solvents. And non-aqueous solvents can be further divided into organic solvents and other molecular solvents, such as hydrogen fluoride, liquid ammonia, and sulfur dioxide, etc. Solvents other than water are collectively referred to as non-aqueous solvents. Most ionic solvents are high-temperature Mordan cells that can be divided into electrolytes and ionic liquids that have recently received a lot of attention. Water is a very excellent solvent for electrode reaction and is widely used. On the other hand, when the electrode reaction uses a suitable solvent other than water, various effects different from aqueous solution can be obtained. For example, the water insoluble substance can be dissolved. Unstable substance in aqueous solution due to reaction with water can exit stably. The electrochemical reaction can be measured in water, a wider potential range, pH range, and temperature range than aqueous solutions. By changing the dissolution state and the reactivity of the solute, the reaction mechanism can be made to be more compatible with the target applications, etc. Electrochemical methods are also the most basic and effective meaning of resolving the properties of the solvent itself and the behavior of the solute in it. Before discussing solvents for electrode reactions, let's review the physical quantities of permittivity and the relative permittivity. Permittivity epsilon is a constant determined by the response produced by atom in a substance when an electric field is applied from outside. The relative permittivity epsilon r is the ratio of the permittivity of a medium to the permittivity of a vacuum. It is dimensionless quantity. The relative permittivity epsilon r of a solvent is the most important properties affecting the solventization of the ion and the dissociation of electrolytes. The solventization energy of an ion is related to several elements of the ion-solvent interaction, of which the electrostatic solventization energy delta GeL can be expressed by the following bronze formula, where Ze is the charge of the ion, r is the radius, n is the Avogadro's constant, and epsilon r is the relative permittivity. Assume that r is a constant in this equation. The absolute value of delta GeL decreased as epsilon r decreases. However, the decrease in the absolute value of delta GL is relatively gentle in the range of epsilon r above 20, but shows a sharp decrease in the range of epsilon r below 10. Since the electrostatic solvation energy delta GeL accounts for most of the total solvation energy of ions, solvents with small relative permittivities generally have a weaker solvent effect on ions due to their smaller absolute value of electrostatic solvation energy delta GeL. In addition, the cations and the anions in solution can be exist in a dissociated state that enable the solution to conduct electricity, or they can be combined as ion pairs, as shown in equation 2. Assuming that the constant for association reaction between the solventized cation and the solventized anion is Kass, log Kass can be roughly expressed by the following forces formula. From equation 3, it can be seen that log Kass is almost linearly related to the inverse of alpha epsilon r, and it can be predicted that if the relative permittivity is smaller or the nearest distance between ions is smaller, the easier it is to form ion pairs whose solutions have reduced conductivity. Let's have a look at the relationship between the log Kass of tetrabutyl ammonia picorate with a large alpha value and the reciprocal of epsilon r. It can be seen that there is a good linear relationship between them. Assuming an analytical concentration of C molarity for the tetrabutyl ammonia cations and picorate anions in solution, a relationship between the degree of the conjugation alpha and the log Ckas is shown in the dashed line. For example, for 0.01 molarity tetrabutyl ammonium picorate, it can be seen that when the epsilon r of the solvent is above 30, more than 80% dissociation occurs. And when epsilon r of the solvent is below 10, more than 90% is in the form of ion pairs. The reaction of a solid electrolyte dissolving in a solvent and dissociating into free ions can be divided into two steps. The solid dissolves in the solvent to form a solventized ion pair, and the solventized ion pair further dissociates to form a solventized cation and anion. For both processes, the higher the relative permittivity of the solvent, the more likely it is moved to the right side. Solvents used for electrode reactions should be able to dissolve the supporting electrolyte and must be able to dissociate into ions in a significant degrees. So, solvents with a large relative permittivity above 20 are usually used. Some typical solvents used in electrochemistry are listed in Table 1, along with their physical properties. It can be seen that the relative permittivity of common solvents used in electrochemistry, such as acetonitrile, DMF, PC, DMSO, and methanol, are much higher than 20. In particular, water has a very high epsilon r, making it a very good solvent for the electrochemical measurements. Solvents used for electrode reactions should be able to dissolve the supporting electrolyte and must be able to dissociate to a considerable extent into ions. So, solvents with a large relative permittivity epsilon r above 20 are often used. However, for these solvents with a low relative permittivity, such as THF, etc., electrode reaction measurements can also be carried out using a suitable supporting electrolyte. Table 2 shows the solubility and the resistivity of the solutions of tetra-alkyl ammonia salts in acetonitrile, DMF, DME, and THF at concentration of 0.6 or 1.0 molarity. The solubilities and the resistivities in the table shows that for acetonitrile and the DMF, which have relative permittivity much greater than 20, the tetra-alkyl ammonia salts dissolve well in the solvents, giving electrolyte solution with low resistivities. However, for DME and THF, which are solvents with small relative permittivity, if the alkyl group of the ammonia salt is acyl, the solubility of these electrolyte salts in the DME and the THF solvents is smaller and difficult to dissolve, and the resistivity of the solution cannot be measured. However, when the alkyl group of the ammonia salt is butyl, their solubility in DME and THF solvents increases considerably, and the resistivity of the solution can be measured. The electrode donor and acceptor properties of solvent, along with the relative permittivity, are factors that affect many reactions and the equilibria that occur in solutions. In particular, when comparing the solute behavior of various solvents with large relative permittivity used in electrode reactions, the effect of difference in the donor and the acceptor properties of the solvent can be more significant than the effect of difference in relative permittivity. As a measure of solvent donor and the acceptor strength, the donor number Dn and the acceptor number An, advocated by Goodman, are widely used. The donor number is measured by the amount of heat of the product produced when the sample solvent reacts with antimony pentachloride in a weak donor dichloroethane as shown in equation 6. And the larger the Dn value, the stronger the donor of the solvent. On the other hand, the acceptor number is measured if there is such an interaction between the dissolved triacyl phosphine oxide in the sample solvent and the solvent, in which case the NMR low magnetic field shift delta of phosphorus 31 is measured using N-hexane as a reference. The acceptor number in N-hexane is defined as 0. The acceptor number of the interaction between antimony pentachloride and triacyl phosphine oxide in dichloroethane is expressed as 100. The acceptor number of the solvent can be calculated by equation 7. The larger the value, the stronger the acceptor of the solvent. Table 3 shows the donor and the acceptor numbers of some solvents in increasing order of donor number. The donor and the acceptor numbers are the strengths of the solvent as Lewis bases and the Lewis acids. Interacting with the antimony pentachloride and the triacyl phosphine oxide respectively, which are also closely related to the strengths of Bronsted base and acid respectively. The solvent with larger donor number means more basic, and the solvent with larger acceptor number means more acidic. However, there is little correlation between the number of donors and acceptors of a solvent and the relative permittivity. Solvents are usually classified in terms of Bronsted acid base, which are classified according to how easy it is to lose or gain protons. Table 4 is an example of Professor Cosford's solvent classification. Amphoteric solvents are solvent molecules that are both acidic and basic. If the solvent is represented by SH, the solvent molecule can release protons and can also accept protons in this way. Among the amphoteric solvents, those with similar acidic and basic strengths as water are neutral solvents. Solvents that are much more acidic and less basic than water, such as sulfuric acid, hydrofluoric acid, formic acid, acetic acid, etc., are proton-donating solvents. On the contrary, solvents that are less acidic and more basic than water, such as ethylene diamine, ammonia formate, etc., are protonophilic solvents. On the other hand, non-protonic solvents generally have only hydrogen atoms bonded to carbon atoms, so the properties of releasing protons and providing hydrogen bonds are weak. However, for alkalinity, there is a difference between strong and weak. Strong bases are protonophilic, while weak bases are protonophobic. Among the non-protonic solvents, these with large dipole moments and relative permittivity are polar non-protonic solvents, which are usually used in electrode reactions. This is because protons and hydrogen bonds are hardly involved in the reaction in these solvents, which makes many phenomena possible that are not possible in protonic solvents, for example, water. Among the polar non-protonic solvents, acetonitrile, propylene carbonate, etc. are protonophobic solvents with little affinity for protons, while these solvents of DMF, etc. are protonophilic solvents. In reactions where the basicity of the solvent plays an important role, these two groups of solvents exhibit distinctly different properties and therefore need to be chosen appropriately for the purpose. The solvation of ions involves multiple factors of ion-solvent interactions that are interrelated. These factors include electrostatic interactions expressed by Brown's equation, donor-acceptor interactions, interaction with the anion through hydrogen bonding provided by the solvent, interactions as hard and soft acid-base, interaction of electrons from D10 cation feedback to the solvent molecules, interactions due to structure formation and structure destruction of the solvent. The energy generated by electrostatic interactions accounts for a large proportion of the total solvation energy, but for the more commonly used solvents with large relative permittivity, other facts tend to have a great influence on the solvation energy. The solvation of cation is generally closely related to the donor nature of the solvent, and tends to be stronger in solvent with large donor numbers. For example, Figure 2 shows the free energy of transfer of potassium ions from acetonitrile to other solvents as a function of the solvent donor number in frame circle, and the hydrogen electrode potential in various solvents as a function of the solvent donor number in solid circle. It can be seen that the hydrogen electrode potential, which has a linear relationship with the dissolution energy of hydrogen ions and the solvation energy of potassium ions, both have an almost linear relationship with the donor number of the solvent. Anion solvation is closely related to the acceptor nature of the solvent. The higher the acceptor number of the solvent, the stronger the solvation of the anion. For example, Fig 3 shows the linear variation of the solvation energy of chloride ions with the acceptor number in a non-protonic solvent. Usually, small anions such as fluoride, chloride, and hydroxide ions, as well as acetate, which with negative charges concentrated on small oxygen atoms, have strong hydrogen bonding acceptability, so they have strong solvation in water or alcohol. However, In non-protonic solvents, which hydrogen bonding or fouling is impossible, the solvation for these ions are weak, and they are in a rather high reaction state. For some large anions, such as the iodide ion and the perchlorate ion, their solubility in water and alcohol solvents becomes weak because of their weak ability to accept hydrogen bonds. However, due to the stronger the polarity, the stronger the dispersing force between the non-protonic solvents with similar polarity. This is why the solvation energy of perchlorate ions in water and alcohols are not much different from those in non-protonic solvents. Water molecules can form hydrogen bond between them, so their entropy value is low. When hydrophilic ion, many inorganic ions are hydrophilic, enter the water, the overall structure of the water around the ion is disrupted due to the strong interaction between the water molecules and the ions, which increase their entropy. However, when hydrophobic large ions such as tetrachloroammonium ion and tetraphenylboric acid ion enter the water molecules will further combine with the ions in their distant surrounding to increase their hydrogen bond structure, making their entropy decreased. As a result, these hydrophobic macro ions become unstable in water, while they can be more stable in organic solvents without hydrogen bonding structures. For this reason, tetrabutylammonia perchloride and tetrahexylammonia perchlorate, which are almost insoluble in water, are well soluble in organic solvent and can be used as supporting electrolytes. When considering Lewis acid-base interactions, it is necessary to distinguish between the hard and soft properties of acids and bases. In other words, hard acids and hard bases, soft acids and soft bases are prone to interact with each other. Even in the solvitization of a metal ion, this effect may be evident. For example, Figure 4 shows the half-wave potential of a metal ion in the coordination of the hard base NNP, whose oxygen atom is coordinated to the metal ion, and the soft base NMTP, whose S atom is coordinated to the metal ion. These half-wave potentials are based on the half-wave potential of the bisphenyl-chromium complex, as the bisphenyl-chromium complex are considered to show almost constant value regardless of the solvent. It can be seen that the solvation of metal ions in the two solvents, that is, the solvation of sodium ion and the potassium ion of hard acid in hard base NMP is strong. However, soft acid copper ions and silver ions has a higher solvation degree in soft alkaline NMTP solvent. A similar phenomena was also observed in DMF and DMTF. Acetonitrile has relatively small donor number, so the solvation of the metal ions in acetonitrile is generally weak. However, unlike monovalent metal ions such as silver and copper ions in acetonitrile solvents, they have very strong solvation and stability. This is because herein the electrons are backdonated from the metal ion to the nitrile group. Therefore, silver and the monovalent copper ion are not easily reduced to metals in acetonitrile solvent. The dissociation of the HA-type acid in the solvent can be divided into two steps as shown in equation 8. The first step is the entry of HA into the solvent as a solventized ion pair. In the second step, the solventized ion pair is further dissociated into the solventized H plus ion and the A minus ion. The equilibrium constant from the ionization process in the first step is denoted by Ki, and the equilibrium constant for the dissociation process in the second step is denoted by Kd. The ionization equilibrium constant Ka, obtained by the potentiometry or conductivity method, can be expressed by equation 10. By substitution, we can obtain equation 11. As a result, both Ki and Kd need to be large in order for Ka to become large. This means that both processes, ionization process of the acid HA and the dissociation, must occur easily. During ionization, the solvent acts as a donor and an acceptor in the order M, HA, in solvent. And the HA bond breaks and becomes a solventized H plus and a solventized A minus ion pair. This reaction process is more likely to occur if that HA bond itself breaks more easily, or if the solvent is more solventized with H plus and A minus ions. In addition, it is evident from the previous mentioned fourth equation that the larger the relative permittivity of the solvent and the larger the closest distance between the H plus and A minus ion, the earlier the dissociation of the solventized ion pair will be. As a result, the relative permittivity of the solvent and the solventization energy of the ion are important factors in determining Ka. For HA-type acids, in addition to dissociation reactions, such homogeneous conjugation reaction can also occur. Table 6 shows the pKa of the acid in some solvents, as well as the homogeneous conjugation reaction constants indicated in parentheses. Water has relative strong donor and acceptor properties and a large relative permittivity, making it a solvent that readily dissociates acids. On the other hand, solventization of H plus is difficult to occur in acetonitrile solvents, which are weak in both donor and acceptor properties, and the solventization of A minus ion is often difficult to occur as well. Therefore, the pKa of the acid is large and there is almost no acid that can be completely dissociated. On the other hand, in DMSO, which has strong donor property, H plus is strongly solubilized so that pK is smaller than acetonitrile, and acids such as picric acid, which are relatively easy to solventization anion, can be completely dissociated. Table 6 shows the dissociation of the BH plus type acid, and the pK of here also shows that the dissociation of this type of acid is influenced by the intensity of the solvation of BH plus, B, and H plus, with the solventation of H plus having a relatively large effect. Thus, the pK in acetonitrile is much larger than in DMSO. pK in DMSO is usually approximately the same as that in aqueous solution. In polar organic solvents, as in aqueous solution, it can be achieved by combining a weak acid HA with its conjugated base A-, or a weak base B with its conjugated acid BH+, to make a pH buffer solution. The dissociation of the BH plus type is usually simple, as shown in the above formula, so the relationship between the composition and the buffer capacity of the BH plus B buffer solution in polar organic solvent is similar to that in aqueous solutions. However, in HA type buffer solution, HA and A- can form Ha2-, slow homogeneous conjugation reaction. Figure 5 shows the effect of homogeneous conjugation reaction on the titration curve of HA acid with tetraacyl ammonia hydroxide. When there is no homogeneous conjugation reaction, the titration curve is a straight line. With the increase of the conjugation reaction constant Kf, the titration curve will deviate from the straight line to a great degree. The relationship between the composition and the buffer capacity of HA- type buffer solution is complex, and homogeneous conjugation reactions occur when both HA and A- have low solubility and are more reactive. In the previous table 4, the solvents were divided into two main categories, amphoteric and non-protonic. If amphoteric solvents are denoted by SH, the self-ionization reactions that occur can be expressed as follows. Similar to the self-ionization reaction constant Kw of water, the self-ionization constant Ksh, that is, the concentration product of these two ions, can be used to indicate the difficulty of the reaction. For non-protonic solvents, generally, due to very weak proton-donating properties, it is difficult to obtain the chemical composition corresponding to the S- ion. Even if weak self-ionization can occur, the obtained Ksh value is often not very accurate. The self-ionization constant of water at 25 degrees, that is, the ion product of water, is 10 to the minus 14 power, and the pH range that can be used for measurement is 0 to 14, roughly. Also, according to the Ksh value obtained above, the measurable pH range of various solvents is shown in Fig. 6. The pH value is based on the aqueous solution, and the minimum pH value in each solvent is expressed by the activity coefficient of hydrogen ion transfer from water to organic solvent, which is equivalent as shown in equation 12. The similar the donor number of a solvent, the weaker its basicity and the wider its acidic region. The similar the number of the acceptors of a solvent, the weaker its acidity and the wider its basic region. Hydrophobic non-protonic solvents have a wider range of acidity and basicity than water, which can be utilized. A stronger acid in a solvent with a wider range of acidity, or a stronger base in a solvent with a wide range of basicity, can exist in its original state without reacting with the solvent. This can be used for differential quantification of mixture of strong acid and base in non-aqueous solvent titrations, but strongly acidic and strongly basic substance as intermediates or products can exist stably when appropriate solvents are used in the electrode reaction, which is one of the important reasons for using organic solvent for electrode reactions. As an electrolyte for electrochemical measurement, it should have considerable solubility in the solvent so that the electrolyte solution may have sufficient conductivity. The measurable potential range should be wide. It must also meet the conditions of not reacting with the solvent or various substances participating in the electrode reaction or causing adverse effects such as changing the electric double layer. Therefore, the variety of supporting electrolytes available for using in organic solvent is rather limited compared to those used in aqueous solutions. For details of the supporting electrolytes used in various solvents, please refer to the reference 1 and 11. The supporting electrolytes shown in Table 7 can be used in various of organic solvents. Of these, the most widely used are tetraalkyl ammonia perchlorate, especially the cheap and easy to obtain tetraacyl ammonia perchlorate and tetrabutyl ammonia perchlorate because they are easily dissociated into ions and have a wide measurable potential range for mercury and solid electrodes. Adverse effects on electrode response are minimal. However, perchlorate presents an explosion hazard when dry. Care must be taken. In recent years, instead of perchlorate, the use of tetrafluoroborate, celled hexafluorophosphate, and trifluorate are increased, especially in the study of oxidation reaction of this cell has been shown to be superior to perchlorate. In low relative permittivity solvents such as DME and THF, it is difficult for the electrolyte to dissolve and dissociate into ions, so there are even fewer types of electrolyte available, but even in these solvents, those electrolytes with large ionic radii of the anion and the cation are still well soluble and provide considerable conductivity. Please refer to the table 2. The potential range that can be used for electrode reaction measurements depend greatly on the solvent and the supporting electrolyte, as well as the type of electrode used for the measurement and its surface condition. The potential limits in the positive and negative potential directions will be introduced using mercury and platinum electrodes as examples, respectively. The limits of the negative potential directions are discussed first. For mercury electrode, due to the large overpotential of hydrogen at the mercury electrode, except for acidic solvent, the cations that normally support the electrolyte are reduced before the solvent. Since tetraalkyl ammonia ion can be reduced to amalgam and exist stably, they are suitable as supporting electrolytes for reduction reactions. This amalgam can exist relatively stably as a thin film on the electrode surface in non-protonic solvents such as acetonitrile and dimethylformate, but it reacts immediately with water in aqueous solutions. Since alkali metal ion can form stable metal amalgam with mercury, reduction can occur at a positive potential of 0.5 to 1 volt above the tetraalkyl ammonia ion. In the mercury electrode, the negative potential limit does not change much even if it contains impurity water molecules. For platinum electrodes, in protonic solvents, such as in the presence of water, the limit of negative potential is the potential at which hydrogen is produced by the reduction of water. However, in non-protonic solvents, the reduction of cation in the supporting electrolyte tends to become the negative potential limit. The reduction potential of alkali metal ion can vary greatly depending on the strength of their solubility and may be more positive or more negative than the reduction potential of tetraalkyl ammonia cations. Alkali metal ions are reduced in many non-protonic solvents and deposited on the electrode, but when sodium, lithium ions, etc. act as cations supporting the electrolyte in a strong donor HMPA, the blue solvated electron generated from the electrode surface enter the solution and become the limit of the negative potential direction. The blue-black background part of Table 8 shows the limits of measurable negative potentials of platinum electrode in various solvents. It can be seen that in many cases the negative potential range of the platinum electrode is wider than that of the mercury electrode. However, a characteristic of platinum electrodes is that protonic impurities, like small amount of water, can have a significant effect on the potential limit. Fig 7 shows the effect of water content on the residue current at the platinum electrode in PC solvent. In propylene carbonate solvent, the negative potential limit gradually moves in the positive direction as the concentration of water increases. At the same time, the positive potential limit moves in the negative direction. For these reasons, the potential limit of the platinum electrode changes significantly depending on the purity of the solvent. The limits of the positive potential direction are discussed next. For mercury electrodes, the limit of positive potential is the oxidative dissolution potential of mercury. When perchlorate is used as supporting electrolyte, the positive potential limit is 0 to 0.4 volt. In the presence of halogen ion, the oxidative dissolution potential of mercury shifts in the negative direction, especially in non-protonic solvents, where an anion solubilization is difficult to occur. As can be seen from the red background in Table 8, for platinum electrodes, if perchlorate is used as a supporting electrolyte, the oxidation of the solvent itself becomes the limit in the positive potential direction. In strong donor solvents like DMSO, DMF, etc., and is limited by the oxidation potential of the perchlorate ion if the solvent is a weak donor solvent, such as acetone nitrile. As can be seen from the table, tetrafluoroborate and hexafluorophosphate are more suitable for the measurement of oxidation reaction than perchlorate. For example, the positive potential limit of the perchlorate ion in the nitromethane solvent is plus 2.3 volt, while the tetrafluoroborate anion is plus 2.9 volt. In protonophobic non-protonic solvents, for example, propylene carbonate, etc., the total measurable potential range can reach about 6 to 7 volts. In aqueous solution, even when measured with a mercury electrode in the negative potential direction and a platinum electrode in the positive potential direction, the overall measurable potential range is below 5 volts. Therefore, from the point of view of the potential range, organic solvents are more advantageous, and those various electrode reactions that are not possible in aqueous solutions can be carried out in organic solvents. The property of the solvent, the supporting electrolyte, and the changes in behavior of both will have various effects on the electrode reaction. Let's first look at the effect of the solvent on the electrode reaction. The potential of a metal ion to be reduced to metal or metal amalgam will move towards the negative potential direction with the enhancement of the solvation of metal ion in the solvent. And there is a thermodynamic correspondence between the negative shift of this potential and the solvation energy. The effect of solvents on porographic half-wave potentials is often used as a means of comparing the dissolution energy of metal ions. Since the decomposition caused by the solvent is not easy to occur in the non-protonic solvent, the alkaline earth metal, aluminum, zirconium, and other ions that cannot get a good porogram due to hydrolysis in aqueous solution can also obtain beta reduction waves. Reactive metals that react with water, such as alkaline metal, can also be precipitated on the electrode in a non-protonic solvent. In non-protonic solvents, the low-valence metal complex produced by electrode reaction can exist stably. For example, the bi-pi-radial complex of ferrous ion undergoes 2-electron reduction in aqueous solution to form zero-valent ion complex in one step. But in non-protonic solvent, 3 steps of 1 electron reductions occur. A reversible reduction step yields a relatively stable complex anion as follows. The same applies to various complexes such as chromium, nickel, and lutetium bi-pi-radial complex. This is because the acidity of the non-protonic solvent is weak and it is difficult to react with the ligand of the complex. These reaction systems deserve attention from the point of view that solvent independently potential reference standards can be obtained. Furthermore, since this complex and organometallic compounds that are insoluble in water are usually soluble in organic solvents, therefore, these electrode reactions can be investigated in details. Many organic compounds are reduced by 2 electrons in aqueous solution to generate the hydrogenation reduction product RH2 in one step. However, in an aprotic solvent, the mechanism of the reduction reaction is divided into 2 1-electron reduction steps. First, a 1-electron reduction generates a very stable anionic radical, and then 1 electron is further reduced to an R2- anion. This phenomenon is very important in the history of the application of organic solvents in electrode reactions and has been extensively studied. The researchers found that with the increase of the accepted number of the solvent, the half-wave potential of anionic radicals generated by reduction in the first step will move linearly in a positive directions. Aoyag et al. Used a platinum electrode in a DME solution of 0.4 molarity tetrabutyl ammonium perchlorate to realize 4 1-electron reversible redox steps of the cyclodecanoate molecule and a relatively stable active anion equivalent to R4- was obtained in DME. Also, in polar protonophobic aprotic solvents such as acetonitrile, polypropylene carbonate, etc., by using an appropriate supporting electrolyte, it can be measured to very high positive potentials, even the oxidation of benzene, which is difficult to oxidize and can be observed. Oxidation of organic compounds often results in the generation of cationic radicals in the first step, which are usually more unstable than the corresponding anionic radicals. In protophilic solvents and aqueous solutions, these cationic radicals react with the solvent. However, in a protonophobic solvent, polymerization of radicals can occur, since no reaction occurs between the solvent and the cationic radicals at this time. Therefore, It is necessary to use a solvent with a suitable strength of the donor property to achieve the target reaction with performing oxidation reaction measurements. The effect of supporting electrolyte on the electrode reaction is introduced below. Since the cation and the anion, the supporting electrolyte, react with species or products of opposite polarity, there are various effects on the electrode reactions. When metal ion from ion pair or complex with the anion in the supporting electrolyte, the reduction potential of metal ions becomes more negative. In aprotic solvents that do not readily solvate anions, or in solvent with low permittivity, this effect will be quite pronounced. Figure 8 shows the influence of the cation of the supporting electrolyte on the polarographic reduction wave of sodium ions in the HMPA solvent. When the supporting electrolyte cation is tetramethyl ammonia or tetraethyl ammonia ion, the sodium ion cannot be reduced at all, and only residue current can be seen. When the supporting electrolyte cation is tetrabutyl ammonium ion and very small reduction waves which have the same characteristics as reactive currents. When the radius of electrolyte cation is further increased, such as lithium ions, etc., the reduction waveform of sodium ions is close to the reversible diffusion-controlled waveform. This phenomenon can be qualitatively experienced as follows. At negative potential, cations with small radii are preferentially attracted to the electrode surface, while larger cations cannot approach the surface due to the presence of smaller cations. When the electrolyte cation is slightly larger, such as tetrabutyl ammonia ion, this effect becomes smaller and some sodium ion is reduced close to the electrode surface by osmosis or dissolution. When the cation is further enlarged, there is almost no interference effect and a diffusion-controlled reduction wave is obtained. It can be seen that the impact of the cations of the supporting electrolyte on the reduction of metal ions at a negative potential is very significant in the strongest donor HMPA and in solvents such as DMSO, DMA, and DMF with strong donor properties. A phenomenon commonly seen in the reduction reaction of alkaline metal and alkaline earth metal ions. However, this phenomenon is less pronounced in weak donor solvents such as acetonitrile or propylene carbonate. The cations of the supporting electrolyte also has an effect on the reduction of organic compounds. Here, in a protic solvent, the ionic radical of the first step reduction products of the reduction reaction of organic compounds has the property of easily forming ion pairs with various metal ions, so that metal cells can be used as supporting electrolyte, or metal ions can be added to the tetra-alkyl ammonia salt solution during the measurement of the parallelogram as shown in Figure 9, where the first reduction wave shifted to a positive potential. The ion pair generation constant can be found from this halfway potential of the positive shift. It can be found that the smaller the radius of the metal ion becomes, or the higher the number of charges, or the smaller the donor solvent like acetonitrile or propylene carbonate, the more likely the positive shift of the halfway potential occurs. We know that the formation of such ion pairs promotes the disproportionation and the polymerization reaction of anion radicals. Therefore, sodium and lithium-ion salts are not suitable as supporting electrolytes for measuring the reduction reaction of organic compounds. In the reaction in this second step, where the anion radical further gains an electron to form a two-valent alkyl anion will be more susceptible to the influence of the supporting electrolyte cation than the reaction in the first step. When alkali metal ions are present, the reduction potential becomes significantly more positive, which can be attributed to the fact that the two-valent alkyl anion forms ion pair with the supporting electrolyte cation more readily than the anion radical. On the contrary, when the radius of the tetraalkyl ammonia ion increases, the reduction potential gradually shifts in the direction of the negative potential, and the reason for this seems to be that the effect due to the change in the structure of the double layer should be considered. Previously, we have discussed the various properties of solvents and the supporting electrolytes and their influence on electroreactions. In addition to these effects, other important conditions need to be considered in order to select a suitable solvent and supporting electrolyte for the purpose of the reaction. Since solvent and supporting electrolytes are used in large quantities, it is very important to be able to purchase them at a suitable price or to be easily synthesized. Solvents and electrolytes should be substantially free of toxicity or hazard during purification and use. In order for the electrode reaction to proceed effectively, the viscosity of the solvent should not be too high, and to take into account the type of supporting electrolyte in order to avoid the viscosity of the solution increased. By using an appropriate organic solvent, the measurement can be performed at a low or high temperature, so that the measurable temperature range is much wider than that of aqueous solution. For example, the measurement at low temperature can allow those chemical species that are unstable at room temperature to exist stably, which is the conducive to the analysis of the electrode reaction mechanism. Furthermore, this solvent electrolyte system can be used to develop batteries that can be used at low temperatures. In summary, when choosing an appropriate solvent as a solvent according to various conditions, we can first consider protonophobic solvents such as acetonitrile propylene carbonate, protonophilic solvents such as DMF, DMSO, etc. If you feel that these solvents are not suitable, or if a more suitable solvent is available, you can also use other solvents. Although we have focused on aprotic solvents in this lecture, protonic solvents such as water and alcohol tended to give better results, and the aqueous organic and the organic solvent mixture can be very useful in many cases. In particular, when mixed solvents are used, solvents' properties can be obtained that are not available with a single solvent and in a wide variety. It is expected that the use of such mixed solvent systems will gain widespread interest. The introduction of this article is summarized below. This is the end of this introduction. Thank you for watching.